Hi student, today we are going to discuss about 12th standard physics, lesson number 4, electromagnetic induction and alternative current, part 3 class. In this video we are going to talk about self-inductance and mutual inductance. Let's see self-inductance. First of all, you tell me what are the inductors. This is nothing but it is a device. Understand? Inductor, it is a device. So the property of inductance produce an opposing induced EMF. When the current flowing through the coil changes is called self-inductance. Understand? The property of the inductor produce opposing of induced EMF when current is allowed to pass through the coil. The property of the inductor is inductance. So it is denoted by capital L. This inductance is used to generate EMF in the circuit when the current in the circuit is slightly changed. That is, changes. Current in the coil changes. In inductor, energy is stored in magnetic field. Understand? Okay. Some examples are coil, solenoid and toroids. Now see, this is a coil, circular type of coil, and this type of coil toroid, and the last one is solenoid, the coil of solenoid. Okay, then self-inductance. How to produce self-inductance? Now consider coil of solenoid. This is a solenoid of coil connected in series battery. So listen, this is a battery and a key. One more component we are connected in variable resistance. We call it is rheostat. This is a rheostat. Okay, now key is pressed. Because of key is pressed, that means closed circuit. So current flowing through the coil and produced magnetic field around it. This is a magnetic field. North pole of the magnetic field. This is a south pole of the magnetic field. This magnetic field linked with the coil in this same coil. So students, the magnetic flux of the magnetic field is linked with that coil itself. This magnetic flux is changed by changing the current. Now see, now here small alter the current, changing the current, and also magnetic flux also changed. This magnetic flux linked with the coil itself. So here EMF is induced in that same coil. Understand? The EMF is induced in that same coil. This is known as self-inductance. The EMF induced is called self-induced EMF. Understand students? Okay. Now magnetic flux, it is denoted by phi b. You know that magnetic flux of phi b. Phi b, the magnetic flux linked with each turns of the coil. Each turns of the coil is directly proportional to current. Directly proportional to current. So students, now listen to it. Magnetic flux is directly proportional to current. Phi b is directly proportional to current. Okay. Now tell me total flux linked with the coil. Number of turns. Total flux linked with the coil is N phi b. N phi b is directly proportional to I. Now proportionality is cancelled. Therefore, N phi B is equal to Li. What is L? This is constant proportionality. L is the constant proportionality is called a self-inductance. Is called a self-inductance of the coil. It is also called a coefficient of self-inductance. Coefficient of self-inductance. Okay. Now find out self-inductance. L is equal to N phi B divided by I. This is a formula of self-inductance. Okay. Now when the current is changed, because of current changes with time, an EMF is induced in it. That is itself. According to Faraday's law of electromagnetic induction. According to Faraday's law of electromagnetic induction. Now see, self-inductance, simply inductance of the coil is defined as magnetic flux linked with the coil when 1 ampere current flowing through the circuit. Understand students? 1 ampere current flowing through the circuit. When the current changes with the time, an EMF is produced according to Faraday's law of electromagnetic induction. This self-induced EMF is given by E is equal to, already you know that, EMF is equal to minus N d phi by dt. N d phi is nothing but that is equal to self-inductance Li. Before equation, N phi B that is equal to Li. Now substitute N phi B is equal to Li. So E is equal to minus D into Li divided by dt. Now calculate self-inductance of the coil. Therefore, EMF is equal to minus L. L is a constant proportionality. Self-inductance is a constant, di by dt. Therefore, self-inductance is equal to minus E divided by di by dt. This is called a self-inductance of the coil. Therefore, negative sign indicator, that means self-induced EMF always oppose the change in current with respect to time. Changing the current with respect to time. Okay, now the current, 1 ampere current flowing through the circuit per 1 second. Per 1 second. Therefore, that value of current di by dt is equal to 1 ampere per second. Therefore, then L is equal to minus E. This is nothing but a inductance of a coil is also defined as the opposing induced EMF in the coil when the rate of change of current through the coil 1 ampere per second. Next, we are going to calculate unit of inductance. Now listen to it. This is a inductance of the coil. L is equal to N phi B divided by I. Already you know that. What is the unit of magnetic flux? Phi B. This is nothing but Weber. Divided by, what is the unit of current? Ampere. Therefore, unit of self-inductance of the coil, Weber by ampere. And one more calculate in another unit. This is also same formula. Self-inductance of the coil, L is equal to minus E. E is nothing but induced EMF divided by di by dt. Now tell me, what is the unit of EMF? That is nothing but volt. Divided by, what is the unit of current? Ampere. Divided by per second. That is current per second. So this is nothing but 1 volt second per ampere. This is another unit of self-inductance. Then calculate 1 Henry. This is nothing but self-inductance. The inductance of the coil is said to be 1 Henry if a current change at the rate of 1 ampere per second induce an opposing induced EMF of 1 volt on it. So, if di by dt that is equal to 1 ampere per second, that value is 1 ampere per second flowing through the circuit, and EMF this is minus 1 volt, then L is equal to 1 Henry. This is a 1 Henry. Self-inductance of the coil is 1 Henry if a current changing at the rate of 1 ampere per second, induce an opposing induced EMF 1 volt in it. So this is a sometime ask 2 mark question. Define 1 Henry. Next topic, self-inductance of a long solenoid. This is important one. Listen student. Let us consider a solenoid of n turns with a length L and area of cross section A. So students, length of the solenoid L and area of cross section A. Now the current passing through the solenoid, listen, electric current passing through solenoid of the coil and produced magnetic field lines. This is a magnetic field. This magnetic field almost uniform and is directed along toward the axis of the solenoid. So students, the magnetic field at any point inside the solenoid is given by, already you studied about in third lesson, solenoid, the magnetic field at any point inside the solenoid is given by B is equal to mu naught Ni divided by L. Now here, number of turns per unit length is given by N divided by L is equal to small n. Now substitute here the magnetic field at any point inside the solenoid B is equal to mu naught Ni. Mu naught means permeability of medium, permeability of free space. Ni, that is a magnetic field inside the solenoid. Okay. Now the magnetic flux passing through each turns. So student, already you know that magnetic flux or magnetic field lines of force passing through the area of solenoid is given by, what is flux, magnetic flux? So this is nothing but a phi. Phi B is equal to magnetic field lines of passing through the area. Okay, now listen to it. This is a magnetic flux is equal to integral of B into dA vector. B vector into dA vector. This is a vector quantity. Now write it, magnitude of magnetic flux, BA cos theta. What is the angle of magnetic field and the area? Here both are parallel to each other because of the uniform magnetic field directed toward the axis of the solenoid. So theta is equal to 0. Therefore cos 0 is equal to 1. So therefore phi B, that means flux, magnetic flux is equal to BA. Now substitute magnetic flux. Magnetic flux phi B is equal to magnetic field inside the solenoid mu naught Ni into A. Mu naught Ni into A. So this is a total magnetic flux linked with the coil of solenoid. Okay. Then total number of turns because of N, capital N. N is equal to, that means N phi B is equal to NL. That means capital N is equal to NL. Number of turns per unit length, that is equal to small n. N is equal to NL into mu naught Ni into A. Therefore, N phi B is equal to mu naught N into N square into A L into current. That is small I. Already we know that N phi B is equal to Li. Now substitute this equation. Okay, now substitute N phi B is equal to mu naught N square L A into I. Now substitute the value of N phi, that is equal to Li. That is equal to Li is equal to mu naught N square A L into I. Now I is I cancel. Therefore L is equal to mu naught N square A L. Understand? Okay. This equation, it is clear that inductance of the coil is directly proportional to square of the turns, that is density. N is the density of the turns. Cross sectional area is directly proportional to area of the cross section and length of the solenoid, and the medium is present inside the solenoid. This is a permeability of free space. Suppose you filled with a dielectric medium. If the solenoid is filled with a dielectric medium of relative permeability mu r, relative permeability, that means mu r. Therefore dielectric medium, this is mu, permeability of medium. Therefore L is equal to mu N square A into L. Mu is equal to permeability. Already you know that permeability of medium is equal to mu naught into mu r. You studied about a third lesson, permeability, mu naught. Now substitute here. This is a mu naught mu r into N square Al. So dielectric medium. Understand? This topic, it is very important one. A 3-mark question. Energy stored in an inductor. Already we have seen that current is allowed to the solenoid. Listen students. The current passing through the coil of solenoid, what will happen? Tell me. An magnetic field produced. When the current changes, and magnetic flux also changes because of magnetic field lines, as per Faraday's law of electromagnetic induction. So students, the magnetic flux is changing and produce induced EMF. So this induced EMF is given by E is equal to minus L di by dt. So this EMF, function of EMF, oppose the changing current. So students, whenever current flow through the solenoid, the self-inductance L oppose the growth of current. Hence some work done or some work has to be done by the external agents in establishing the current. This work done is stored as magnetic potential energy. So students, now here assume resistance of the inductor is negligible, only effect is considered. So induced EMF at any instant of time E is equal to minus L di by dt. So okay, The small amount of work done dW moving a charge dq in a time interval dt. So therefore dW is equal to minus E into dq. Already you know that electric current I is equal to charge per unit time. What is the charge? dq is equal to I into dt. This value substitute this equation. Therefore dW is equal to minus E into I into dt. Okay, then now substitute induced EMF. So this induced EMF E is equal to minus L into di by dt. Okay, now substitute here. Therefore dW is equal to, it's nothing but small amount of work done, minus into minus L into di by dt into I into dt. Now dt into dt is cancelled. Therefore dW is equal to L I into di. Okay. Now calculate total amount of work done. The total work done in establishing the current I is given by total work done W is equal to integral of dW. Now taking integral on both sides, dW is equal to Li into di. So integral of dW is equal to integral of Li into di. Therefore initial to final integral value, initial current 0 and final current I. Okay, now L is a constant, self inductance is constant because of self inductance of the coil. Okay, now tell me, already you know that integral value of I into di, that is equal to I square divided by 2. This is a integral value of I into di. Now substitute here, this is a I square divided by 2, lower limiter to upper limiter. Okay, now substitute the limited value. So upper limiter to lower limiter. This is W is equal to 1 by 2 Li square, substitute upper limit minus lower limit, because of 0 the total is 0, so this is a neglected. So total work done, therefore W is equal to 1 by 2 Li square. This is a work done is stored as magnetic potential energy. It is denoted by magnetic potential energy UB. UB is equal to 1 by 2 Li square. Okay. Now the energy density. Now calculate the energy density is the energy stored per unit volume of the space and is given by, what is the energy density? It is denoted by UB. That is equal to capital UB divided by volume of the solenoid, area into length of the solenoid, A into L. Okay, now substitute the value of UB, that means energy stored, potential energy. Okay, now 1 by 2 Li square divided by AL. Okay, already you know that L, because of L is equal to mu naught n square A into L. We are discussed before topic. Okay, now substitute here. Therefore UB, small ub is equal to mu naught n square AL into I square divided by 2 AL. Now AL is cancelled. Therefore UB is equal to, small ub is equal to mu naught n square I square divided by 2. So okay. Now tell me students, what is magnetic field at any point inside the solenoid? Now see, this is a magnetic field at a inside the solenoid. B is equal to mu naught Ni. Okay. B square is equal to mu naught square N square I square. Now substitute B square divided by 2 into mu naught. So this is called a energy density. This is called a energy density. Next topic, we are going to talk about mutual inductance. whenever there is a change in magnetic flux linked with the coil. Listen to it. Changing the magnetic flux linked with the coil, there is also change of flux linked with the neighboring coil. Understand? Change of flux linked with the neighboring coil producing an induced EMF in the second coil. This phenomenon of producing an induced EMF in a coil due to change in current in the other coil is known as mutual inductance. So students, in another definition, when an electric current passing through the coil changes with the time and EMF is induced in the neighboring coil, this phenomenon is known as mutual inductance and the EMF is called a mutually induced EMF. Listen to it. Okay. Then consider two coils. This is coil 1, this is coil 2. Now coil 1 we call it is primary coil, across connected to the AC source. This is a positive terminal and a negative terminal. And a second coil, this is a coil 2, we call it is secondary coil, across connected to external devices, is nothing but galvanometer. Okay, now if an electric current flowing through the coil C1, now here magnetic field produced by also linked with the coil 2. So students, now current is flowing through the primary coil, we call it is coil 1, this is I, and magnetic field is produced. This is north pole of the magnetic field and this is south pole of the magnetic field. This magnetic field linked with the coil 2. This is nothing but magnetic flux linked with the coil 2 and EMF is produced. So in magnetic flux linked with the coil 2, now see, this is a magnetic flux linked with the coil 2 due to coil 1, therefore phi 2 1, therefore phi 2 1. So magnetic flux linked with the coil 2 is directly proportional to current I, we call it is I1 because of primary circuit, is nothing but coil 1. This is a magnetic flux linked with the coil 2 is directly proportional to current I1 in the coil 1. Therefore flux phi 2, the magnetic flux linked with the coil 2 due to coil 1 is directly proportional to I1 in the coil 1. Okay. Now n number of turns because of total flux linked with the coil 2 is directly proportional to current in the coil C1. So this is a N2, number of turns of the coil 2, N2 into phi 2 1 is directly proportional to I1. Now proportionality is cancelled. Therefore N2 phi 2 1, N2 phi 2 1 is equal to M21 into I1. Here M21, M is nothing but constant proportionality, we call it is mutual inductance of the coil 2 with respect to coil 1, that is called a M21. It is also called a coefficient of mutual inductance. Understand students? Okay. Now calculate mutual inductance of the coil. It's nothing but coefficient of mutual inductance M21 is equal to N2 phi 2 1 divided by I1. So this is called a coefficient of mutual inductance. Okay. Now if 1 ampere current Now taking this is a I1 value, 1 ampere current flowing through the coil C1, coil 1. This current produce magnetic field. Changing magnetic flux linked with the coil 2 when 1 ampere current flow through the circuit because of coil 1. Therefore, mutual inductance M21 is equal to N2-Phi21. So this is a mutual inductance. Once again, the mutual inductance M21 is defined as the magnetic flux linked with the coil 2 when 1 ampere current flow through the coil C1. Flow through the coil 1. That is called a primary coil. Okay. Then when the current changes, I1 current changes with the time, and EMF produced in coil 2, that EMF E2. This is a E2. According to Faraday's law of electromagnetic induction, this mutually induced EMF E2 is given by E2 is equal to minus D into N2-Phi21 divided by dt. Already you know that N2-Phi2 that is equal to M21 into I1 before equation. Okay. Now M21 is constant. Now taking outside, therefore E2 is equal to minus M21 di1 divided by dt. Now calculate coefficient of mutual inductance. Therefore M21 is equal to minus E2 divided by di1 divided by dt. So in this above equation, a negative sign indicated. This negative sign indicates that the mutually induced EMF always oppose the changing current I1 with respect to time. Understand? So therefore M21 is equal to minus E2 divided by di1 divided by dt. If there di1 divided by dt, that is equal to 1 ampere per second. 1 ampere current flowing through the circuit per second in 1 second. Because of current flowing through the circuit in 1 second, then the mutual inductance M21 is equal to minus E2. Are you clear? Okay. Then mutual inductance is also defined as the opposing EMF induced in the coil 2. E2 is nothing but coil 2 induced EMF when the rate of change of current through the coil when is 1 ampere per second in coil C1. Understand? Okay. Then similarly, when a current flowing through the coil 2, now see the current flowing through the coil 2, we call it a secondary coil, and produce magnetic field. Now listen to it. This is a magnetic field. North pole of the magnetic field, south pole of the magnetic field lines. This magnetic field interact with the neighboring coil C1. We call it is coil 1. This magnetic field linked with the neighboring coil and produced induced EMF. We call it is E1 because of primary coil of induced EMF E1. So if an electric current I2 through the coil to change with the time, EMF E1 is induced in coil C1. Therefore M12, so M12 that is equal to N1-Phi12 divided by I2. Now calculate what is N1-Phi12, that is equal to EMF. So and M12 is equal to minus E1 divided by, that is induced EMF. E1 is nothing but induced EMF in coil C1 divided by di2 divided by dt. So M12 is mutual inductance of the coil C1 is nothing but coil 1 with respect to coil 2. It can be shown that for a given pair of coil, the mutual inductance is same. Therefore, M21 is equal to M12, that is equal to M. In general, the mutual inductance between two coils depends on size, shape, the number of turns of the coil, the relative orientation and permeability of the medium. Understand? Next, find the unit of mutual inductance. Now taking the equation M21 is equal to N2 521 divided by I1. Already you know that what is the unit of magnetic flux of Weber, that is Weber divided by what is the unit of current, ampere, Weber by ampere. So this is also same thing, Weber by ampere in mutual inductance, that is equal to 1 Henry. So unit of mutual inductance is also Henry. This mutual inductance between two coils, coil 1 and coil 2, is said to be 1 Henry if current of 1 ampere in coil 1 produce unit flux, that is magnetic flux linkage in coil 2. Therefore, di by di1 divided by dt, because of 1 ampere current per 1 second. So this is a value 1 ampere per second. Now the induced EMF of the coil 2, 1 volt. So then the mutual inductance 1 Henry, that is mutual inductance 1 Henry. Therefore M21, that is equal to 1 Henry. So student, the mutual inductance between two coils is 1 Henry if a current changing at the rate of 1 ampere per second, 1 ampere per second, that is equal to di1 divided by dt is equal to 1 ampere per second in coil C1. We call it is coil 1. Induced an opposing EMF 1 volt in coil 2, that is E2 is equal to 1 volt. So understand students, this is a 2 mark questions. Note it down. Now we are going to discuss one more important topic, mutual inductance between two long coaxial solenoid. So in previous section we have discussed mutual inductance. What is mutual inductance? Is defined as the opposing induced EMF in the coil 2 when the rate of change of current through the coil 1 is 1 ampere per second. This is mutual inductance. Okay, now consider two long coaxial solenoid of same length. This is a two coaxial solenoid. This one is the solenoid 1, this is a solenoid 2. The number of turns of the solenoid 1 N1, number of turns of the solenoid N2. Now length of the solenoid L. Both of the coil or solenoid is same length. The length of this solenoid is large when compared to the radii, so that the magnetic field is produced inside the solenoid is uniform and the fringing effect at the end may be neglected. So students, now here the area of the cross section, let A1 and A2. So this is A1 is greater than A2 because the greater area of cross section of the solenoid 1 compared to solenoid 2. So let A1 and AB the area of cross section of the solenoid with A1 being greater than A2. So students, the turn density N, small n, these solenoids are N1 and N2 with respectively. This is a density, turn density N1 of the solenoid 1 and N2 of the solenoid 2. So okay, now let current, the coils 1, the solenoid 1, I1 current flowing through the solenoid 1, then the magnetic field produced inside the solenoid. Now see, here the magnetic field is produced. Already you know that this is a solenoid. Magnetic field at any point inside the solenoid is given by B1 is equal to, because of solenoid 1, B1 is equal to mu naught N1 into I1. So as the field lines of magnetic field lines B1 are passing through the area bounded by solenoid 2, the magnetic flux linked with each turns of the solenoid 2 due to solenoid 1. Understand students? The mutual inductance of the coil of the solenoid 1 and 2. Here the magnetic field is produced, coil 1, and this magnetic field passing through the area bounded by solenoid 2. The magnetic flux linked with each turns of solenoid 2 due to solenoid 1 and is given by, what is magnetic flux? So that is phi21, because of magnetic flux of the coil 2 due to coil 1, solenoid coil 1. Therefore phi21 is equal to integral of B1 vector into dA vector. Now write it in magnitude form, B1 A2 cos theta. Here magnetic field and area of the cross section both are parallel, so angle is 0, cos 0 is equal to 1 is nothing but phi21 is equal to B1 A1. Now substitute the value of B1, therefore mu naught N1 I1 into A2. This is a flux. Then the magnetic flux. The magnetic flux linked with the coil 2, with a total number of turns. Total number of turns of the coil 2, N2 phi21 is equal to, this is nothing but N2. N2 is equal to small n2 into L. Now substitute here into mu naught N1 I1 into A2. So N2 phi21, that is equal to mu naught N1 N2 A2 L into I1. From this equation phi2. Now total number of magnetic flux N2 phi21 is equal to mu naught N1 N2 A2 into L into current I1 in coil, the solenoid of the coil 1. Therefore already you know that N2 phi21 is equal to M21 I1. Now substitute here, therefore M21 into I, that is equal to this one, mu naught N1 N2 A2 L into I1. Now I1 I1 is cancelled. Therefore, mutual inductance of the solenoid 2. Therefore, M21 is equal to mu naught N1 N2 A2 into L. So, this above equation mutual inductance M21 of the solenoid 2 with respect to solenoid 1. Understand, students? M21 of the solenoid 2 with respect to solenoid 1. Then similarly we can find the mutual inductance of the solenoid 1 M12 with respect to solenoid 2 as given below. The magnetic field produced by the solenoid 2 when current carrying conductor I2 is given by, therefore B2 is equal to mu naught N2 I2. Now the magnetic field is uniform, the solenoid 2, but outside the solenoid 2 is almost 0. Now understand, student, the magnetic field B2 uniform inside the solenoid 2, but outside the solenoid is almost 0. Therefore, solenoid 1, the area A2 is the effective area over which the magnetic field B2 is present, but not area A1. Then the magnetic flux 512, now listen to it, this is a magnetic flux 512 linked with the each turns of the solenoid 1 due to solenoid 2. Therefore, flux 512 is equal to integral of B2 into dA. So, now write it magnitude form B2 into A2. Now substitute the value of B2 mu naught N2 I2 into A2. Are you clear, children? Now the total magnetic flux linked with the coil, that means solenoid 1 with the total number of turns N1 is given by, therefore N1 512 is equal to, this is nothing but N1 is equal to small n1 into L. Now substitute here mu naught N2 I2 into A2. So now N1 512, that is nothing but M12, this is nothing but M12. Now write here N1 512 is equal to M12 into I2, that is equal to this one. Now I2 is cancelled. Therefore, mutual inductance of the solenoid 1 due to solenoid 2. Therefore, M12, that is equal to mu naught N1 N2 A2 into L. So students, from this equation M21 is equal to, now again write here M21, that is equal to mu naught N1 N2 A2 into L. A2 into L, and here also M12 is equal to same magnitude. M12 is equal to same magnitude. So students, in general, the mutual inductance between two long coaxial solenoid is given by, so this is M12 is equal to M21, that is nothing but M. In general, mutual inductance between two long solenoid coaxial solenoid is given by mu is equal to, that means M is equal to mu naught here now write it mu naught n1 n2 a2 into L. So n1 mu naught n1 n2 a2 into L. So this is a final equation. Suppose if a dielectric medium of relative permeability mu, relative permeability, this is a mu r, is present inside the solenoid. Therefore, now write the equation mutual inductance of the two long coaxial solenoid mu n1 n2 a2 into L. What is mu? Mu is equal to permeability of free space into relative permeability mu r. Now substitute here m is equal to mu naught mu r n1 n2 a2 into L. So students, this is a mutual inductance between two long coaxial solenoids. Understand? This is dielectric material of this equation. This is permeability of free space equation. Next, tell me students, answer my question. First question, what for an inductor is used? Give some examples. Second question, define self-inductance of the coil in terms of magnetic flux and induced EMF. Third question, how will you define the unit of inductance? This is important. 3 more question, note it down. And fourth question, an inductor of inductance means L, carry an electric current, how much energy stored while establishing the current in it. And fifth question, it is a very important 5 mark question, note it down. So that the mutual inductance between a pair of coils is same M12 is equal to M21.